Hi, in this video I'm going to show you an example using Biot-Savart Law. This is just another way of calculating the magnetic field, or rather B, the magnetic flux density. And in fact, we're going to compare two different ways of calculating it from this in this example. So it's just a formula for calculating B. And Biot-Savart Law looks like this. The magnetic field at some location R, so that R being a vector, that makes it a three-dimensional location point that's just written in the vector shorthand, is equal to mu naught I over 4 pi integral around a contour, in particular a closed contour because physically currents tend to go in closed contours. At DC, there's no way for current to flow because of charge conservation unless the circuit is closed. Of dl cross a hat r, that's the unit vector in the direction from the observation point to a location on the current, divided by big R squared. And there, big R is equal to the magnitude of R minus R prime, where R is the observation point, and R prime is a location on the source. So at any particular location of observation, all of the points on the source distribution are going to provide us some contribution to the magnetic field. Now I've written down R with no vector on it as the scalar magnitude of the difference between those two vectors. I'm also going to define R the vector, big R the vector, as the difference between those two little r vectors. So little r minus little r prime. So that's the vector from that point on the source distribution to the observation point. Vector from source to observation point. All right. You can also look at the differential contribution from a small piece of the loop. And that small piece of the loop would be I, the current carried by the loop, times dl, the length and direction of that little tiny piece of the loop. And that would be equal to dB, a differential contribution of the magnetic. Never likes it when I write B's. I'll try it one more time. dB, there we go, a differential component of the magnetic field. And that would be equal to mu naught I over 4 pi dl prime, because remember primed coordinates are on the source distribution, cross a hat r over big R squared. So like I said, a hat big R is in the direction of big R, and big R not a vector is, as I showed you up here, and big R the vector is over here. Now, there's one other way to write this differential contribution which is useful to us, and that is, we can also write dB this way. Mu naught I over 4 pi dl prime cross big R divided by big R cubed. All I've done is write that unit vector a hat big R as big R the vector divided by its magnitude. So that's pretty straightforward. Now, the example that we're going to do is example 5-3. We have a current I, which is on a straight wire, and it has length 2L, and we're supposed to find the magnetic field B, or the magnetic flux density, at a point R, some distance from the wire, in the plane that bisects the wire. Now let me draw a picture of that. Here's what that looks like. We have our wire like this, and here is the plane that bisects the wire. I'm drawing a side view. We only want the magnetic flux density there. We don't care what it is anywhere else. Now this wire has length 2L, so it has length L above the plane and length L below the plane. Now, since we only care about that particular plane and we want to know B as a function of distance from the wire, we have a sort of cylindrical symmetry here. We can define this line, the line containing the wire, as the Z prime axis, or really the Z axis, because we're going to have the primed coordinates exist on the location of the wire. And that means that what we care about here is a distance R away from the wire. And we're not going to care about any points up here that are not on that plane. Now, they would like us to find this in two ways. Part A is using the magnetic vector potential, and part B is using the Biot-Savart Law. So, first, let's do part A. Now, I want to warn you right now, there's a long integration in this one, so if you want to pause and get a glass of water and settle yourself in, maybe grab some popcorn, it's going to take a while. All right. That said, step one, as usual, we want to choose a coordinate system. In this case, we kind of already chose it by drawing the diagram. It's going to be cylindrical. Part two, we're going to use the integral formulation for A. And that is, insert some math here. A is going to be equal to, I'm going to explicitly write down that A is a function of R. Now little r, as I've written it here, is not a vector because remember that is the radial component of distance away from the z-axis in cylindrical coordinates. So we're not making we're only finding A as a function of that distance, not as a function of 3 dimensions. So we're only going to know A in the plane. Now that is equal to A hat Z mu naught I over 4 pi integral from minus L to L dz prime. Remember, these primed coordinates range all over our source distribution, and in this case, the source distribution is on the z-axis from minus L to L. Square root of z prime squared plus little r squared, where z prime squared plus little r squared is equal to my big R. Now, if I wanted to draw a picture of what exactly that looks like, again, I've got my line source here. We care about A in this plane with the dots. R is some distance out to here. R. We're going to have some particular region dz prime at a height z prime. This line carries a current I in the z direction. That's where we got the z-directed unit vector there. And so if I want to know the distance from that point on my source distribution to the observation point, big R, this is a right triangle, so big R is equal to square root of z prime squared plus little r squared. There we go. Those are all the important bits of our diagram here. Now, we can solve this integral, that integral, using substitution and also some triangles. It's going to take a long time, so get ready. I'm mostly doing this because everybody could use some integral practice, no matter who we are. So let's get started. So to begin with, A is equal to mu naught I over 4 pi integral. I'm going to substitute u is equal to z prime over r here, and then du is equal to dz prime over r. So then if I do that, I'm going to integrate from minus L over R to L over R du over square root of 1 plus u squared. Now, if you want to just skip this entirely, this integral of 1 over square root of 1 plus u squared du is equal to ln of u plus square root of 1 plus u squared. And that should be in absolute value marks. But I'm going to walk you through the steps to get there because that is not intuitive at all. This is a weird one. Just warning you now. All right? So what we're going to do is we're going to actually substitute again. We're going to say that u is equal to tangent theta. And that means that du is equal to du d theta. Here, I'll just write this bit out too. Du d theta is equal to derivative with respect to theta of tangent theta, that's going to involve some product rule stuff. So that's derivative with respect to theta of sine theta times 1 over cosine theta plus, more space, derivative with respect to theta of 1 over cosine theta times sine theta, which is equal to, the first term in that evaluates to cosine theta divided by cosine theta, which is nice because that just, oh man, it crossed out all my stuff. Cosine theta over cosine theta, which is nice because that just becomes 1. And then the second term is equal to sine theta times minus 1 over cosine squared theta times minus sine theta. Woo! Am I going to be able to fit my parentheses in there? Yeah, mostly. All right. That whole thing, if you simplify it out, is equal to 1 plus tangent squared theta. Now remember, I was writing that is the derivative of theta with respect to, derivative of u with respect to theta. So, du divided by 1 plus tangent squared theta is equal to d theta. Remember, tangent theta is u, so that's also equal to du over 1 plus u squared. Back to that integral. Now I've got integral du over square root 1 plus u squared. I'm going to multiply top and bottom by 1 plus u squared, and then I get integral of 1 plus u squared over square root 1 plus u squared du over 1 plus u squared. Now's my time to substitute in theta. Now I've got 1 plus u squared divided by square root of 1 plus u squared gives me positive, on top of the fraction, square root of 1 plus u squared. Remember that u is equal to tangent theta, so then I've got square root of 1 plus tangent theta, tangent squared theta, sorry. And remember, du over 1 plus u squared is equal to d theta. So that's my integral at this point. Now there's a trig identity that we can use, and that is that 1 plus tangent squared theta is equal to 1 plus sine squared theta over cosine squared theta. And that 1 can be written as cosine squared theta over cosine squared theta. We got to add that sine squared over cosine squared there. So that, if we simplify using cosine squared plus sine squared equals 1, then what we have is 1 over cosine squared theta. Then what we end up with is the square root of 1 plus tangent squared theta is equal to 1 over cosine theta. Cool. Next, now what we have is integral d theta over cosine theta. Nice. Now what? More substitution. At this point, no one would blame you if you looked it up. You've got it in a pretty simplified form, and this is the kind of thing that shows up in integral tables all the time, so it's not hard to deal with, but we're going to do the whole thing. So this is also, we can write the 1 over cosine theta as secant, so that is secant theta d theta there. We're going to do another substitution, and this one is not very intuitive. It's kind of weird, but that's okay. We're going to choose v, because we already used u, as secant theta plus tangent theta. Then dv is equal to secant theta times tangent theta plus secant squared theta. If you want to verify that one, you're welcome to. I'm not going to do that derivative out just now because I don't want to take the whole day. All right. Now when we're evaluating this integral, we're going to first just multiply by v over v again. So we've got secant theta times secant theta plus tangent theta divided by secant theta plus tangent theta d theta. Sorry, this dv needs to have a d theta at the end. There we go. Now if you take a look at this, you can see that on the top we actually have dv and on the bottom we have v. See, like I said, it's not an intuitive substitution, but then it comes out looking really nice. Then our integral is actually just equal to 1 over v dv. How pretty! Which is equal to ln of v, technically ln of absolute value v. At this point, what exactly is v? We've done a couple of different substitutions, so let's review. We have that tangent theta is equal to u is equal to z prime over r. And remember that secant theta is equal to square root of 1 plus tangent squared theta is equal to square root of 1 plus u squared. So then that result, ln of v, becomes ln of u plus square root of 1 plus u squared. That u was tangent theta and the square root of 1 plus u squared is the secant theta. And we're going to evaluate that from minus L over R to L over R. When we do that, we end up with ln of L over R plus square root of 1 plus L over R squared divided by minus L over R plus square root of 1 plus L over R squared. Cool. In order to make this look nice and to have the same format as they ended up with in the book so that you can compare, we're going to multiply the through on the top and bottom by R. Remember that multiplying by R, the R becomes an R squared inside the square root. So then you get ln of L plus square root of R squared plus L squared divided by minus L plus square root of R squared plus L squared. That was a lot, but the end result then becomes our solution for A, the magnetic vector potential, is A hat Z mu naught I over 4 pi ln of all that stuff, square root of r squared plus L squared plus L divided by square root of r squared plus L squared minus L. We drop the absolute values because this turns out to be positive, so it's fine. And then we have to find the magnetic flux density, and we remember that B is equal to curl of A. A is z-directed, so we only care about the parts of the curl that operate on A sub z, the z component of A. So then we have B is equal to A hat R, 1 over R, partial AZ partial phi, minus A hat phi, partial AZ partial R. Now that first term goes to 0 because there's no phi dependence in our expression for A. You can go back up and verify that by looking at it. There's no phis in this equation here. In that case, B is just going to be minus A hat phi partial derivative with respect to R of all that stuff minus mu naught I over 4 pi ln of square root L squared plus R squared plus L over square root L squared plus R squared minus L. There, just barely had enough room for my parentheses that time. I'm not going to evaluate that derivative right now because we are otherwise going to end up with a super long video. But what you get, if you use lots of chain rule and product rule, you get that the derivative with respect to R of ln of L squared plus R squared plus L over square root L squared plus R squared minus L is equal to minus 2 L over R divided by square root L squared plus R squared. Now, that means that finally our magnetic field is equal to A hat phi mu naught I L over 2 pi R 1 over square root L squared plus R squared. So there we go. That was kind of long. And the reason that we did it is to make the point that that was kind of long. Sometimes it's more advantageous to use the vector potential A, and sometimes it's more advantageous to use Biot-Savart Law. So for part B, we're going to use Biot-Savart Law. Again, here's the expression for the law. B is my B's always disappear. Is equal to mu naught I over 4 pi. I'm going to use the expression for dB that uses the r cubed on the bottom. So then that would be dl prime cross vector r, big R, divided by r cubed. For this situation, remember that the vector r is equal to A hat r times r minus A hat z times z prime, and dl prime is equal to A hat z dz prime. So then dl prime cross r is equal to A hat z dz prime, sorry, that's a subscript there, cross A hat r times r, because when you cross a z-directed unit vector with the z component of something, you don't get anything, you get 0. So that cross product evaluates to a hat phi r dz prime. Then our integral then looks like mu naught I over 4 pi integral from minus L to L a hat phi r dz prime over z prime squared plus r squared, that's the magnitude of big R, to the 3 halves. Well, the square root of that stuff is the magnitude of big R, which is why we have the 3 halves there. So, this one also we do using a substitution. First of all, we're going to do u is equal to z prime over r, and that would be du is equal to dz prime over r, meaning that then we have integral of r dz prime times r cubed times, divided by there, z prime over r squared plus 1 quantity to the 3 halves. You see what I did there? I factored out an r squared, and then when I took it outside of the 3 halves exponential, it became an r cubed. And if I want to write that in terms of u, remembering that dz prime is equal to r du, then I end up with 1 over r times integral of du over 1 plus u squared to the 3 halves. Again, we're going to use u equals tangent theta, which means that du equals secant squared theta d theta. And we're going to use the fact that 1 plus u squared is equal to 1 plus tangent squared theta is equal to secant squared theta. With all of that, then we end up with our integral becoming 1 over r integral of secant squared theta d theta over secant squared theta to the 3 halves, which is equal to, I don't want to drop my 1 over r, 1 over secant theta d theta. Remember, secant theta is 1 over cosine theta, so now we just have integral of cosine theta d theta. So that's equal to 1 over r times integral cosine theta d theta. Integral of cosine is sine, so what we have here is sine theta over r. Let's review what exactly is sine theta. We'll go back to that picture here. Here we have z prime, here we have r. This was theta because remember u is equal to z prime over r is equal to tangent theta. So then sine theta is going to come from this z prime end of the triangle. So sine theta is z prime over square root z prime squared plus r squared. Because remember, this side of the triangle is big R. So with all that, we now have magnetic flux density is equal to a hat phi mu naught I over 4 pi r z prime over square root of z prime squared plus r, little r squared from minus L to L. We're evaluating z prime on those bounds, which is equal to a hat phi mu naught I over 4 pi r times L over square root L squared plus R squared minus L over square root L squared plus R squared. So then our result, B, it really hates the way I write B's, is equal to a hat phi mu naught I over, 2 pi r, because we combine these two, we add them together, and we get a 2L on top, times L over square root L squared plus R squared, which is the same as we got last time. Same answer, slightly easier integral, Biot-Savart